welcome back. This is our last video in this series for chapter 17 on curved mirrors. So in the last couple you've kind of learned about concave mirrors, and you learned about how to draw ray diagrams, and you haven't had a lot of practice drawing ray diagrams. I understand that. Again, come to Google Meet, come to the meets. Meet number 1, we'll talk about straight plane mirrors, and then meet number 2, we'll talk about curved mirrors and drawing these ray diagrams and give you some practice on that. For this particular one, we're going to be talking about virtual images. So we're going to be using ray diagrams again, but in this case, instead of drawing real images, we'll be kind of figuring out how do mirrors produce virtual mirrors, virtual images, and where they are. So I've got 3 examples of virtual images right here. None of these are real images. These are all images that exist only in the mirror itself. So all of the images produced by plane mirrors are virtual images. You can't project a flat mirror onto a screen, a flat mirror image onto a screen. That vase there, that image of that vase only exists kind of behind the mirror, inside the mirror. But convex mirrors also only produce virtual images, and concave mirrors can produce virtual images as well. Concave mirrors are the ones we did in the last, and most of the time, concave mirrors can produce real images. But if you get close enough to them, concave mirrors can produce virtual images. So we have all 3 of these different kinds. And so today we're going to be looking at concave mirrors, and their virtual images, as well as convex mirrors and how they produce images. So these are a little bit more awkward in terms of drawing these ray diagrams, just because of where the images are formed. They're virtual, so they're behind the mirror, and that makes them a little bit more awkward to do. So here's a real brief overview of kind of what some of these different diagrams are going to end up looking like. And again, I just wanted you to have a sort of an image of what, I don't even know how I can put this out of the way, sort of an image of what this would kind of look like, so you can kind of see these different types. So when we drew plane mirror images, right, we had these images, these rays that were bouncing off of the mirror, and then we had our virtual rays that were extending behind the mirror, and we have our image back there. So all of the images that we produce with plane mirrors in 17.1 are virtual images. With concave mirrors, they have, most of the time, if an image is, if an item is really far away, an object is way out here, it'll produce a real image kind of down here somewhere. But if you sneak that object up real close to the mirror, like a magnifying mirror would do, then all of a sudden you can get something different, where you can get these virtual images that are being formed behind here. So kind of notice what we're doing. We're still having kind of similar rays, right? The real rays are still done in straight lines. And then these virtual rays, and where they meet behind the mirror, is still done in this dashed line format. With convex mirrors, these are awkward as well. This one, I don't like the conventions on that. These should be straight lines. But with convex mirrors, what you end up seeing is a really, really tiny little image. It's adorably small, so small. And this is also behind the mirror. So we'll take a look at how to draw all of these here in just a second. So we'll go through these and kind of practice drawing them. So again, virtual images are behind the mirror. And notice how both of these are upright, as opposed to the real images that were formed by concave mirrors were inverted. They were upside down. So take a look at this. All right, so here's our practice for sort of drawing these guys and starting to get a handle on these. Okay, not the best, but we'll kind of start with this particular drawing. So again, we're going to draw our same 3 rays. Always draw the same 3 rays. Get in the habit of doing that, and it will certainly make your life a lot easier. Again, this particular image is not the best for this, but I was trying to find something that wasn't too complicated looking for a screen. So remember, ray number 1 goes in flat and then bounces back through F. And then ray number 2 went through F and then bounced back flat. And then ray number 3 was the one that just went through C. These same rays should be in here. I know this one's only showing 2 of them, but I'll show you where the 3rd one is. But we're going to go through that same convention for drawing these. So ray number 1, again, goes in flat, and then it bounces through F. So if you lay it out, it goes in flat, and it should go all the way to here. And then it bounces through F. F is now behind the object. So it's going to reflect back downwards and behind. So there's your ray going down there. This is ray number 1. And again, it's the reflected ray that you extend back behind here in those dashed lines, because that's a virtual ray. But again, it's not the incoming ray. It's always the reflected ray. It's not the incident ray. So again, the dashed line goes back behind there. Okay, ray number 2. Ray number 2 should go through F, and then bounce back flat. So the hardest thing about this is to lay this one out correctly. So F is back here. So you literally lay your ruler basically from F through the tip of this, and then it's going to kind of extend up this way. So it's kind of going to go like that is what that ray is going to do. And then it's going to bounce back straight parallel with C. And it should go this direction that way. And again, this is the one that is not shown in this particular drawing, is that second ray. So again, you're going to line up your ruler through F and through the tip of the object, and it's going to go up and hit the mirror, and it's going to reflect back parallel to the principal axis, and the reflected ray, again, is virtually reflected back behind the mirror. And then ray number 3 is the ray that's lined up through C. And so you can see that one is on here, starts here, it goes through C and then back through C. So it's going to go all the way through there, line up your ruler through C, and then the virtual one comes through this way. And they should all kind of line up at that one particular spot over there. So with doing this, again, it's the same 3 rays every single time. And if you can kind of get in the habit of always drawing those same 3 rays, it's going to make your life a lot easier to be able to kind of interpret these. So let's talk about in terms of our conventions and our sign conventions for this. So we have HO and then we have DO over here. So remember that HO is the height of our little pencil and DO is the distance to our little pencil. So both of these guys are by definition considered to be positive, HO and DO. If you take a look at these in terms of the size and the direction, DI right now, I'm going to do HI first. HI is upright. So notice how this one is an upright pencil right here, and this one is also an upright pencil. So by convention, because it is upright, it's considered to be positive. And if you remember from the curved mirror one, the convex ones that we had the real images, when that one's out here someplace and it's upside down, it's a real image, our HI was considered to be negative because it was inverted. So again, here our HI, height of our image, is positive because it's upright. Okay, DI is a little bit weird, and F is a little bit weird. Actually, I shouldn't say F isn't weird yet. F on this side, we haven't talked about F yet, but it becomes important when we start talking about convex mirrors as soon as we throw that in there. By definition, we're going to call the focal point of a concave mirror positive because it's capable of producing real images. So that's the positive F right there. Okay, last one, DI. Now this, remember, is a virtual image. This is not real, and it's on the other side of the mirror from the actual object. So if you think of this as being like an XY axis, if this side here is positive, that means this side here is negative. But more importantly than that, because it is a virtual image, we would consider DI to be negative. And again, because it's a virtual image, it's behind the mirror, so DI is negative. And it looks like in this case that DI is like a little bit further than DO, which is okay. And it definitely looks like HI is larger than HO. So if we take a look at what's going on here with our magnification, remember magnification has 2 different parts to it. It has a sign and then it has like a magnitude. So first things first, because it's bigger, right? It's magnified. We would say that M is greater than 1. It's magnified. In fact, it looks like it's about magnification equal to about 2, just looking at it, right? It's about twice as tall as the original HO was. The second thing is that we would say it's greater than positive 1. And again, it's greater than 1 and positive, which means it's larger or magnified, right? And it's upright. Again, the positive side in magnification tells you that it's upright. The fact that the M is greater than 1 would tell you that it's magnified or enlarged, something along those lines. Again, we're going to practice drawing these during meet number 2, especially these virtual images for concave mirrors. These are a little bit awkward. Most of the time, I'm going to ask you to draw real images, but I will, there'll be 1 or 2 of these. I'm going to ask you on the performance assessment, 1 of the 2 images I'll give you will be virtual. So kind of keep that in mind. So again, sign conventions. For concave mirrors capable of producing real images, it's a positive distant, for its focal length. DI, because it's a virtual image, is negative, and HI, because it's upright, is considered to be positive. So our magnification here is greater than 1 and positive. All right. Convex mirrors have a little bit of a different style. These are the ones that are like the Audi mirrors, right? They're like fisheye kind of mirrors, where you can actually kind of see a much wider field of view. And so these are the ones that allow you to sort of basically see around corners is what convex mirrors do. The reason why you've got a convex mirror, the reason why the objects in the mirror are closer than they appear is because this is actually slightly convex. It helps eliminate that blind spot. It widens your field of view. This is actually a dude did this fairly recently, was impersonating the Escher drawing of a dude holding holding a reflective sphere. So he actually did a personal photograph of it. It's kind of cool. But that sphere in there is acting like a convex mirror of type. And then you can see, like here, we can see around the corner and see what's coming up. So convex mirrors have a little different style in terms of how they produce things. And these are the by far most annoying of the ray diagrams. So, take a deep breath when you're looking at this one on here. Okay. When you're drawing these things, convex mirrors only form virtual images. They're only behind. Only. Convex is the hard one concave is the hard one because sometimes they're real, sometimes they're virtual, depending on where it is. With convex, it doesn't matter. Convex always produces virtual images, always back behind there. The other thing that makes convex mirrors different is because of where the focal point is and the C is. Now, these are virtual focal points. Again, the mirror surface is over here. It's a diverging mirror. This thing does not possibly converge real rays on any spot. So this spot back here is virtual. It's the virtual focal distance. It's not a real focal place. There's no real rays to be able to go through there. It's not like you can concentrate rays behind a mirror, but that's effectively what this ends up doing. That's why when we talk about convex mirrors, the focal length is considered to be a negative number. So if, your positive F is over here, negative F behind the mirror would be, minus 5 centimeters or something along those lines. And it's the same relationship between F and C. This is still 2F. So the center of curvature on the back of that mirror, half of that center of curvature is where that virtual focal point would be back behind the mirror. So that's where that F is. So that's kind of an important piece about convex mirrors. Okay, next thing to keep in mind, we're still drawing our same 3 rays. It is still in flat and then through F, and then through F and then out flat, and then through C. Those same 3 rays are still here. What makes them different now is where the F is. It used to be you'd come in through F, or come in flat and go through F this way. But now you're going to come in flat and F is on the other side because F's over here, right? So take a look at ray number 1. Ray number 1 comes in flat right here. And then you're going to line your ruler up with F behind the mirror. The real ray reflects back up the ruler as opposed to the virtual ray continues down through F. Again, it is still in flat and through F. It is that same pattern. So you go in flat, line up your ruler through F for the second half of it. The real ray bounces up and away, and the virtual ray is the one that extends through to the inside of the mirror. All right, ray number 2. Ray number 2, if you remember correctly, I'm trying to think what they've got in here. Ray number 2 goes through F and then came back flat. Okay, well, the same thing is true in this one. It's just your F isn't on the same side of the mirror. The F is over here now. So what you do is, okay, erase. You line up your ruler with the tip of the pencil and F, which is now back here. You line your ruler up, your real ray goes like this, and then your reflected ray, once it hits that mirror, bounces back flat. It's this one is the reflected ray that continues through. I don't like having this one on there. Don't continue that line because you'll wonder what's going on there. So the real ray comes in through F. Again, F is on the other side. As soon as it hits that mirror, it bounces back flat. And it's the reflected ray that continues behind the mirror on the virtual side. Again, I try not to draw this one if I can, unless you want to draw like little dots or something as like just a lineup for your ruler. But again, this one can really confuse students because they think that there should be an image there and there is not. So again, that's not the one that I like to draw. And then the third ray goes through C. So again, you've got your object, line your ruler up with C on the exact opposite side now, and it goes in like this, and then bounces straight back out, and then virtually continues through right there to C. So what you can see is where those rays converge is on the back side of the mirror. That's the tip of your tiny pencil. And so that's where your image is. Again, your image is formed on the back side of the mirror. These are the ones that are, again, a little bit awkward to draw for a lot of students. So again, what I would really, really, really strongly recommend is not drawing this one. All the other ones, it makes a lot more sense to draw them because where those other rays converge is where the image is going to form, or the tip of that image is going to form. All right, so let's take a look at our conventions here, sign conventions for this and interpreting this. So DO, distance to the object, and height of the object. Again, our object is over here. Those are still going to be considered to be positive. So there's HO, and here is DO. So if we take a look at the other things, okay, DI, it's a little bit smaller, right? It's not, it's a little bit closer to that particular thing. So our image is real small here. But if we take a look at this, is this a real or a virtual image? Because it is a virtual image, DI is negative. And again, because it's a virtual focal point, DI is negative. Okay, HI, if we take a look at our height here, it's small, but it's still upright. So because it's upright, HI here is positive. And again, why? Because that image is upright. So we give it a positive value for HI. And then if we take a look at our magnification, magnification is interpreted the same way. Is it greater than or less than 1? And then is it positive or negative? So it's smaller. So we know that magnification here is less than 1, maybe a half, right? And then it's upright. So we know that it is positive. So again, magnification has a magnitude as well as a sign. So it's smaller. In other words, it's reduced. And then it's upright. So there you go. Ray diagrams for convex mirrors. Last thing I was going to mention is when you're dealing with these two equations, again, these are exactly the same equations. These are no different. But when you're doing the math part of using these equations, you can use these just exactly the same with virtual images. Makes no difference whatsoever. What makes a difference is things like interpreting this, that if you have a convex mirror, that makes sure that your focal distance there is negative, that if you've got virtual images, that maybe your DI is negative. These signs in here with virtual images then become critical to understand what these are. Same thing here in terms of making sure you've got your negative signs, because your magnifications here should end up being upright because your DI is negative. So if you've got a negative negative, this ends up being a positive. So again, the only thing I wanted to mention with these, the equations are exactly the same. Just be ultra careful about using negative signs in the correct spots, and then using your algebra. So if you're adding a positive fraction and a negative fraction, you are subtracting. So some little minor things with that. So there you go. That is the kind of overview of how to draw ray diagrams for virtual images. Hope you enjoyed it, and I will see you at the meets, and we will practice drawing some of these because they're kind of a pain. They just take practice. All right? Enjoy. Talk to you guys later. Have a great day. I hope you're enjoying the sunshine, and spread kindness, not COVID, right?